Okay, so as you probably know, all and everything in this universe, at least the physicists say us, started with Big Bang. So this is how we will start the show as well. And perhaps I'll just do it. You know, this is what we like the most, is not saying about things, but actually doing these things. Interesting, not oxygen, perhaps this one. No. It was better, but never goes as always planned. So if you know what you're doing, you can remain in control, even with hydrogen. So that was explosion. It didn't go quite as explosion, perhaps because I didn't put enough oxygen in there to be mixed. And hydrogen is a very important element because all the energy in this part of the universe comes from hydrogen. Not exactly from chemical reaction, actually from physical process of nuclear synthesis, in which hydrogen, which is the lightest element, is converted to helium. And this is done on the sun. And even the fossil fuels, such as that you get gasoline and so on, and coal, they were generated long ago, but the main source of the energy was coming from the conversion of hydrogen to helium. Now, hydrogen would be a fantastic chemical fuel as well. The reason for it is the product of its combustion in oxygen is water. And water is a good thing. It's something that you can drink, not like carbon dioxide, which causes a lot of havoc in the environment. And by the way, in case you didn't know, as a result of global warming, the model predicts that Nova Scotia will get some cooling. I think this is what we are all experiencing right now. There's a good reason for it, is that all the warm air melts all the ice in Greenland, and guess where the icebergs and all the cold water goes? Goes our way. But maybe summertime will appreciate it. Okay, so we started with hydrogen. Hydrogen belongs to gases, and at one point chemists, who were called alchemists at the time, they thought that there were only 4 elements existing. Now, of course, we discovered there are more than 100, but at the time it was air, which all the gases were considered to be air. There was water, there was earth, and there was fire. So my show will go starting with air, with gases, then we'll go with liquids and solids, and eventually we'll end up with fires. So let me move just one step further for the next element, and that element is helium. So maybe I'll just show what happens if you ignite helium. Actually, I was even louder back, perhaps. But that was not a chemical reaction, it was just the rupture of the rubber. Okay? Chemically, helium is a very inert element. It has very interesting physical properties. I'll try to demonstrate. So what I now did is just inhale helium, and did you figure out that my voice has changed? Perhaps not so much. I'll try to do it again. Perhaps now you noticed or not. It kind of goes up and down, just like a teenage boy there. You know, sometimes it's up, sometimes it's down. Alteration is the result. I think I better gain my voice. Alteration is the result of the change in the speed of sound, which is the result of molecular properties. Helium is a small molecule, not the smallest, but the second small molecule. And therefore, it has very different properties than, say, oxygen or nitrogen, which are normal atmospheric species. If we move further, periodic table, now we have a few metals, then the non-metals, and then the next gas that we have is nitrogen. Nitrogen is pretty inert as well. We always inhale it and exhale it, and nothing happens. It's just a diluent, if you will. Most important gas that we inhale is oxygen. But we have the nitrogen in liquid form. And this is the stuff which is at about minus 200 degrees Celsius. And as liquid, it's very fragile and has very interesting physical properties as well. It can convert some ordinary materials to display some extraordinary properties. Every year I do something new. Last year we were using banana to drive the nails in the board there. This time I think I would prefer to go local, so I brought the cucumber which is made in Nova Scotia. So which one you would prefer to be used as a hammer? Cucumber or banana? Banana is already done, so I know it works. This will be new first time experiment. But I don't know how to do it.
Cucumber, make new science.
Let's try, yeah, let's try something new. Unless somebody would dare to do some experiments, nobody would know what would happen. So put it there and I'll cook it. Actually, maybe I'll do both. And I joined the group of my supervisor, research supervisor. I very quickly learned that it's useless to ask the question, should I do this or should I do that? Because he would always say, try both, and then come and see. I'll put both. Meanwhile, I can show you some other changes. So here we have the flour, not made of plastic, it's just the regular flour. And if I just immerse it, this one doesn't have to be cooked a long time because it's easily attains the properties. Now, being cooled at minus 200 degrees centigrade, it can be broken just like glass. Do you hear the sound of it? Just like that. And of course, it's not only fun, it's actually used in science. Biologists do it in order to break the cells of biological cells and also in order to release the nuclear material and in order to do the DNA analysis. So using the liquid nitrogen and grinding it in very cold temperatures, they can extract DNA and identify these things. So fun experiments and scientific experiments, they are sometimes interchangeable. We can do both things. By the way, don't be fooled that we are doing these experiments every time whenever the chemistry is done. Usually we reserve it towards the end of semester. So this is a delight that you are participating in. Meanwhile, I think I have some of the things already cooked, but I'll put some materials that you know. This is the rubber hose. Very flexible, right? So I'll put it in liquid nitrogen as well. And two identical rubber balls, right? One will be the blank, the other I'll put there and see what happens with it. So I think our cucumber now is ready to go. Looks almost the same as it was. Let's see if it works. Now, this one is in the way. Oh. No. This is what happens sometimes. Actually, it does work, at least to some extent. But not as good as banana was. See, it became so brittle that it just breaks up like glass. And of course, if you have a hammer made of glass, then it's not so good. I think banana is better. This is what we were using all the time. Also cracked, but perhaps I'll use this one better. That one is pretty good, I think. So, take home message, banana are making much better hammers. As brittle as cucumbers. This, of course, it has nothing to do where they are going. Okay, some other materials that we have changed the properties of. So, this rubber, I can use actually the rubber as well to dry the metals now. Should not overdo it. With the nail now, you can see it goes on the other side. So driven, in the beginning, it was driven by banana, and then I had finished the job there with the rubber hose. Now I think my rubber ball is ready to go. So remember, the property was that it was very rubbery, could jump. This one is solid rock. So this is what happens with the tires at very frigid temperatures. If you go in some places, you know, they really can become square, and then as you drive, you will actually feel humps and bumps. Not in Nova Scotia, fortunately. Okay. So another gas there that is very interesting is the carbon dioxide. So carbon dioxide is the result of oxidation reduction reaction. It takes place when you burn the carbon, which is this element. So you burn it in oxygen, you get carbon dioxide, which is in gas, a gaseous substance, but you can actually cool it sufficiently so that it becomes solid. And this is the carbon dioxide, which is a solid material. It's called dry ice because it never gets converted to a liquid. It gets converted right from the solid state to the gaseous state, which is called sublimation process. Interesting thing about it, if you put it in water, then it starts to boil, producing carbon dioxide. And because it has the temperature of about minus 40 degrees Celsius, you obtain a lot of water vapor, sort of like a fog. Maybe I'll put it in a few places for you to see. And it also is acidic, so it forms an acid, and I will try to show you the acidic properties as well. If it works. So here I have a little bit of the alkali solution, which I put in a solution that contains indicator that changes the color. So the color change is the result of the reaction of the substance, which is called indicator, that changes the color depending on pH. And now is basic pH there. You can see the blue color of the bromoform blue. But if I put carbon dioxide, it forms the weak carbonic acid, and little by little the color will change. Maybe sometimes things don't go as planned, but they can be always changed. Knowledge is power. So, carbon dioxide is the main reason for global warming. And this is the substance as it goes and gets converted from the earth state, as the alchemists would call it, to the air state. Now I would like to show you a little bit what I call the kitchen chemistry. And one of my favorite experiments there is the experiment with food that I do on me. So I have a candle. Let me just ignite this candle to show that it is real. Right? And what a chemist with the knowledge of chemistry can do with this candle is eat it. Did you ever see anything like that happening? Do you believe me?
Tasty.
Very tasty. This is the experiment that you can try at home, actually. Because it's just a simple trick. It was not a candle, it was just a piece of banana, just a small piece, and a little small piece of pecan, which was just stuck there, looking like a candle, right? So I ignited the pecan, and pecan has, it's an oily material, and oil can burn in air, right? This is a good fuel. Two of the primary fuels that the marathon runner needs. 70% is fat, which we all, even the slimmest marathoner has enough to run like 3-4 marathons in a row. Okay. Second fuel is sugar. So banana itself had a lot of starch. It was a sugary carbohydrate drink, carbohydrate fuel, and pecan was oil. Now, if you take just the garden variety spaghetti, right? This is what you know, and you eat. Of course, you cook it before you eat. You can ignite it, and you can see that it actually burns. See? And this is what happens in your body as well. So you convert this carbon-containing substance into carbon dioxide and water. And this is the fuel which 30% of which marathoner must use in order to run the race. And actually, you cannot run marathon without refueling during the run. So you must take some of the sugar with you. And if you buy some stuff, actually you can even read, different components in there. These are, you can read how many calories, how much fat, how much carbohydrates, any fuel that you consume, and convert to carbon dioxide use every time. This is the information which is provided by chemists, by the way. Chemists which are analytical chemists, like me. I like actually looking at things and disassembling things more than assembling. All right, now we are moving from the air part of the show to the solids and liquids, which is earth and water part of the show. And I am always mentioning a good saying that I have inherited from my good friend and colleague, Dr. John Roscoe, who was the head of the department here. And he was always saying that physicists and mathematicians, they have only problems. Biologists may have some cultures. Chemists, we have solutions. And literally, we like to do the solution chemistry. We like to do chemistry in the liquid state. Reason for it is that it provides much more control, right? So I will start that, I think, with a little magic. But unlike true magicians, I actually will explain what I'm doing here. Perhaps to put it in between here. Okay. Genie, come on. Come on. Actually, when I was trying it last time, it didn't work. Because, the genie gets old and it has to take some time actually to come out of there. Come on. Oh well. Just in case, I put a lot of stuff, but there is a little bit, but the different stuff they have in here. And I'll explain the differences between them. So this is a plan B kind of thing. Now it works. So what was in there? Of course, this would be just magic there, in medieval times, but we are now Modern times we can explain things, we understand things very well. So what was inside was the hydrogen peroxide, but not the variety you can buy in a store, because we are carefully selecting our chemicals so that they are not as easy to reproduce at home. Besides, of course, the edible candle one, which I think you will be able to impress your friends with. Okay? And what I had initially was the manganese dioxide, and it was supposed to work, but it kind of indeed getting all the crystal structure changes, and therefore it doesn't work as effectively as a catalyst. Okay? So therefore I had a little bit more soluble form, which was potassium permanganate. That requires only just a few crystals in order to accelerate the reaction. And this is just decomposition of hydrogen peroxide. So it converts to oxygen and it converts to water. What you were seeing is just the vapor of water. Didn't have any smell, didn't have anything. There is yet another reaction that can be demonstrated with hydrogen peroxide. We call it the elephant's toothpaste. You have to be careful here. So in this setting, the catalyst is already there, and we have a little bit of soap in order to have it nicely looking. And I have hydrogen peroxide. Oops. Sometimes it does get messy. Well, I'll just leave it right there. Some other experiment that I have prepared is about the conversion and changes in different colors. So here I have a bottle with water, and I can show you that I can convert it to milk. So I just take and pour it there. Now I have milk. And if I don't want milk, I can convert it to water back. Now I have water again. Of course, it was not water. Okay, we had the solution containing calcium ions, and we have the oxalate containing beaker there. It was just a little bit at the bottom so that you don't see it really well out there. And you would form calcium oxalate, which is a white precipitate, which makes it appear as if it is milk. And of course, if you put it in the solution containing strong acid, then it decomposes and you form the water again. And this is this kind of experiments which made me what I am, a chemist. Of course, I saw them at the early, maybe 12 years old time in my life. And I found it so interesting that things would change color and would be easily converted from one thing to the other. It wasn't like a magic for me, so I wanted to learn more, and this is why I became a chemist. And one of my favorite things that I was doing was to have the indicator change the color. And I'm sure you have used indicators before. So this one is interesting that we have two different indicators which have exactly, I would say, opposite colors. So one is red, the other is blue. And if I add acid to both of them, so same substance is added, the color changes pretty much to the same color as in this solution, and then I add the same substance. And now this gets converted to blue color. Kind of a little bit darker there, but perhaps you can see it. If I can put something white behind it, you can see the change of color. So the same substance can make the different indicators change the color. And this is totally reversible. So put in the acid, put in the base now, converts litmus. This is the litmus that is blue in the basic condition to blue color. And another indicator called Congo red is converted to the red color. And of course, it took me years later to understand why it happens. So briefly on fingers, why it happens is just that the electron that moves in the molecule, this is emission, but let me just kind of explain, not in too many details, is that the color depends on the room that electron has to move from one part of the molecule to the other. So if there is a lot of room, it moves and it takes the electron a long time. Therefore, it oscillates at relatively low frequency. And if there is a little room, then it oscillates at higher frequency. So in emission, it's not emission, it's absorption, but I don't want to go in details. Emission would happen at shorter wavelength if you have oscillations which are happening faster with higher frequency. Longer frequency or higher frequencies would result, the lower frequencies, longer wavelength would result in the red color of the solution. It's just the same as in marathon terms. If the person has short legs like myself, then just runs very quickly moving the legs, and if the person has long legs or running with the high heels perhaps, can go much faster there, making just a long strides. So same idea applicable to here. Now suppose you are at the party and you want to treat 5 different people with different juices and you have just one bottle of water. Is it possible there? Well, if you are a chemist, it turns out it is possible. So I have solution that reads water, and I'll pour, and I'll convert this glass. I'll pour milk in that glass, as you can see. And then same bottle, no other tricks. I'll get the apple juice. Overdone it a little bit. Apple juice is always the trickiest one here. Now the lemon juice is easier to make. This is lemon color. Cranberry juice. That's my favorite. And finally, the blueberry juice. So all the different colors. White, this was supposed to be sort of dark yellow, like apple juice, lemon juice, cranberry juice, and blueberry juice. By the way, only the lemon juice is not locally made. We in this valley produce milk, we produce the blueberries, cranberries, apples, and even grapes. So, very good place to live. Anyways, of course it was not water, so I explain, as a chemist I want to explain at least some ideas about what has happened. So this solution here contained a sulfate ion and it contained calcium. So calcium and oxalate, actually this was carbonate I believe, made the milk appearing precipitate, okay, white precipitate. Apple juice was formed when iron 3+ formed a complex with acetate ion, so there was sodium acetate in there. Lemon juice is obtained when you have the tartrate ion, the ion of tartaric acid, which is obtained during winemaking, by the way. Cranberry juice is obtained when iron 3+ interacts with thiocyanate ion, and finally the blueberry juice, the characteristic blue color, is obtained when iron 3+ interacts with the iron ferrocyanate. So different colors can be obtained from the same bottle. One more, and we are kind of going sort of more and more interesting things. Suppose you want to drink water, and here I have the cup, okay? And I will just pour some cold water in it. So water appearing transparent liquid. So pour there. That will be enough. Did you see I did pour there? I think I have to show it. So everyone sees that something goes in. And then suppose I wanted to have a little bit warmer. So I put some warmer water in there, okay? Still water-looking, transparent substance. And I kind of have to mix it a little bit. maybe a little bit of the other one. Didn't work this time. And just pretend nothing happened. It's always the plan B. By the way, these are all harmless chemicals, so I can easily dispose of them. I do fish in the seawater here, and I eat the fish I catch because I know that it is safe. Okay, one water, and then the other water. One more time. If you think that all the experiments work from the first try, you have to become scientists to appreciate that it is not so. You read a scientific paper and you think, oh, I could repeat this experiment in like one day. And people were working on it like years, which is, by the way, true. Because the years are taken to take circles, and all the trials and errors. Well, I'll show you the secret in the end. So pour a little bit of this, and less of this. More. No, less. Okay, we'll try. More works better. Now, I don't think it will be perfect, but you know, real world is never perfect. So anyways, what I wanted to show is that there's almost nothing there, but it didn't work the way it was. Well, I'll show you what is happening, because this is why I have this. So next time we'll make sure that we mix solution better. So we have solution containing calcium acetate in water. I think I poured all of it. And then if you pour ethanol in there, it makes jelly. And it was supposed to be completely solid. Now it's a little bit better. So anyways, it could be completely solid, so when you try to pour it out, it will just get stuck. But it didn't work. It happens sometimes. Reality of life. Now let me show you a little bit more interesting experiment, and I hope that this one does work, because this is truly my favorite one. So, you know, in this valley we were having lots of orchards, and now there is more development of vineyards. So, you know, one industry is, I think, competing with the other, and which industry will win, nobody knows. So here is an experiment in which we will have sort of competition between orange and grape juice. This one to work really well. So far apple juice. Now is the grape juice. So grape juice wins. Right? And actually, maybe the apple juice comes back now. And while you're watching, I'll explain what happens. So here, there are two reactions which are competing, and it's sort of like two runners. You know, once the first person goes ahead of the second person has some chance to rest, right? And then the second person goes ahead of the first one, right? And then this first person has some rest and then goes ahead. And you have seen it in competitions of runners, you have seen it in competitions of bicycle riders as well. So in the same fashion, this is the reaction in which one reaction is competing with the other reaction. So the products of one reaction are catalyzing the other reaction. And as a result, you have the competition between the blue and yellow colors. And in the end, I think the blue color is expected to win. Maybe I'll actually make it a solution in here, because I have some reagents left. Maybe there will be a chance we'll get another observation of the same thing. I'll mix it better this time. This maybe will be showing a little bit better. And now we are approaching the finale of the show, so we will be moving from the reactions with liquids and solids, with what we as chemists like the most, to the playing with fire, so to speak. And I have a sort of a transition there in which I have both. So I have this, what I call chemical cannon. I put a little bit of water in it. Not actually water, of course. Close it like this, and I have the source of ignition in the form of a spark. Works like cannon. So here we put some water and then we have some fire. This is, by the way, the same principle that you use in your cars. Put the fuel in. The fuel was methanol. Actually makes a good fuel, just like ethanol does. Okay, and a spark can ignite it. And as a result, it reacts with oxygen, which is inside here, and it can push a projectile there. Of course, I perfected the design there to make it for my child use there, you know, for the fun. This one is rechargeable, so you can put some fuel there easily, and you can kind of do it again, because usually with this reaction people say, oh, do it again, we wanted to see it again. Should I, or maybe I should not?
You should.
Okay. Once. I'll do it twice and then we'll move on with the other. You need some oxygen there, right? So you have to blow. Oxygen and fuel, both of these things are required for combustion, so something that you'll learn right away here. Let me do it again. Sorry. Okay, so now we have produced some fire there from water, and now I have the two final experiments, in which one will be the chemical volcano, in which I'll ignite what will be looking like almost like a real volcano with a drop of water. And the other is, of course, the gummy bears that everyone likes. But as I said, just as a precaution, I will ask everyone to leave the show just as soon as gummy bears are finished. Okay? We have agreement? All right, I'll replace these glasses with my glass blower glasses. Just for the fun of it. These are actually special designed didymium glasses that allow you to see the yellow color of the flame better. So now I deposit just a few droplets of water-like substance. And with some magic, hopefully this one will work. Now it does, it does, it does. Yes, there we go. So as volcano goes, I'll get the final part. Last time we had 3 colors, but I think we set all the alarms. So this time I will have just 2 colors. It would be yellow color and red color. Does it look like volcano? It does. So the water actually was not water but glycerol is a benign substance, just almost like water is. In fact, it's one of the nutrients. And when you place it on the strong oxidizer such as potassium permanganate, the reaction can go so vigorously that it will ignite, and the flames later on will go with ammonium dichromate. This is this yellow substance which was there, and ammonium dichromate decomposes, forming the green substance called chromium trioxide. By the way, ammonium dichromate is the substance representing hexavalent chromium. This is the one which was studied by Aaron Brockovich, if you have seen that movie. So that yellow substance is the only thing which I would not pour down the drain. But now it is decomposed in chromium-3 substance, which is one of the micro elements. So this green thing is actually required by the plants to grow properly. This is to say that there are no good or bad chemicals, but if you know your chemistry well, you can use things in a good or bad way. Okay, just a little more. So what I'm doing here, I'm melting the strong oxidizer. The reaction can start. The yellow one didn't go well. Now it is. It went well in the end. All right. Thank you very much for your attention. Stay always in control, and if you can run marathon and know chemistry, you can be in control all your life.